But since the pandemic is still persisting, we have had to break with tradition once again. And therefore, in 2021, the D.M. Bose Memorial Lecture is being held in the hybrid mode. Today's distinguished speaker is Professor Amitava Roycaudhuri, who is an emeritus professor from the Department of Physics, University of Calcutta. Professor Roychaudhuri is a stalwart in the area of particle physics. We will begin today's events with a welcome address by Professor Uday Bandopadhyay, Director, Bose Institute. Professor Bandopadhyay, please.
Professor Amitava Roycaudhuri, Professor Soumitra Sengupta, distinguished guests, ladies, gentlemen, my dear colleagues and students, a very good afternoon. On this very special and momentous occasion of 137th birthday of Devendra Mohan Bose, I have the privilege on behalf of all my colleagues at Bose Institute to accord a very warm welcome to all of you. Our special guest today is Professor Amitava Roycaudhuri, who will deliver D.M. Bose Memorial Lecture, which all of you know as an integral part of this memorial celebration. Professor Devendra Mohan Bose, an illustrious scientist who had left a great legacy initiated by his uncle, Acharya Jagadish Chandra Bose. This year, when we are celebrating 75 years of India's independence, Azadi Ka Amrit Mahotsav, remembering such an eminent scientist is very much significant. D.M. Bose had the commitment for development of science in India, tracing the footsteps of our illustrious father, J.C. Bose. This is evident from a letter from Tagore to D.M. Bose. I quote, "The good news that you have taken up the responsibility for guiding Bose Institute has given great assurance to my mind. There is not the slightest doubt that you will light new lamps through your dedicated work. May your great effort find fulfillment in the country's well-being. This is my deepest wish." A letter communicated to Professor D.M. Bose. D.M. Bose was indeed a versatile genius, as evident from the following significant contributions. Physics research at Bose Institute was truly initiated by D.M. Bose and his students, who pioneered high-energy physics research as well as nuclear physics research in India. The most notable discoveries of D.M. Bose was the development of photographic emulsion for the detection of ionizing particles in cosmic rays, and the first experimental indications of the pi meson in cosmic rays, along with his students Viva Chaudhary. In 1947, C.F. Powell used D.M. Bose technique along with full-tone photographic plates, determining the distinct masses of pi and mu meson, and was awarded Nobel Prize in 1950. Powell had, of course, admitted in his book, The Study of Elementary Particles by the Photographic Method, that the method developed by Bose and Chaudhary in 1941 on distinguishing between tracks of proton and meson in an emulsion was indeed the first attempt. Apart from this, D.M. Bose had also initiated experimental studies in Bose Institute on artificial and spontaneous radioactivity. D.M. Bose was also one of the earliest in 1920s, making theoretical and experimental contribution in the area of quantum theoretic explanations of paramagnetism and diamagnetism. During his directorship of Bose Institute, the first department of microbiology in India was set up in 1942. In addition to research in physics, D.M. Bose tried to carry out the physiological investigations in plants at the molecular level using biochemistry. D.M. Bose played a pioneering role in the studies on history of science in India. He also became the editor-in-chief of the Indian Journal of History of Science and was one of the editors-in-chief of A Concise History of Science in India, published by Indian National Science Academy in 1971. He was also the editor of Indian Journal of Physics and Science and Culture. His pioneering achievement made him the recipient of several honors like DSc from Calcutta University, DSc from Jadavpur University, and Deshikattama, the highest award from Vishwabharati University. He had a significant role in national planning, had direct involvement in the formation of Atomic Energy Commission and in India's nuclear program. It was during DM Bose stewardship that the institute really fully blossomed as a modern scientific research organization, starting new departments, initiating research in a number of frontier areas. We all are eagerly waiting for the lecture of Professor Amitava Roycaudhuri. Many thanks, Professor Roychaudhuri, for accepting our invitation to deliver this prestigious DM Bose Memorial Lecture 2021. I am also very much thankful to Professor Soumitra Sengupta for giving us consent to preside over this program. I am sure you all will certainly enjoy the lecture. Thanks for paying attention to me.
Thank you, Professor Bandopadhyay. Today's function will be presided over by Professor Soumitra Sengupta, who is a senior professor at Indian Institute for the Cultivation of Science, where he holds the Amal Kumar Roychaudhuri Chair in the School of Physical Sciences. He is also the Dean of Faculty and Staff Affairs at IACS. Professor Sengupta earned his bachelor's degree from Presidency University and a master's degree from the University of Calcutta. Thereafter, he pursued his PhD degree at Shah Institute of Nuclear Physics. He has held faculty positions at prestigious institutions, Presidency College and Jadavpur University. From there, he moved to the equally prestigious Indian Association for the Cultivation of Science. His research interests include the areas of astrophysics, string theory, and high-energy physics. He has several international collaborations, and over the years, he has received many awards and accolades. He is a fellow of the National Academy of Sciences, India, and was the first coordinator for the member country of the Asia-Pacific Center for Theoretical Physics from India. Sir, we are truly honored by your presence today, and thank you for accepting our invitation. I request Professor Soumitra Sengupta to kindly preside over today's meeting and introduce the speaker. Sir.
Thank you, Professor Sarkar. Thank you, the Director of Bose Institute, Professor Uday Bandopadhyay, Professor Amitava Roycaudhuri, and other members in the audience. It is indeed an honor to introduce Professor Amitava Roycaudhuri, the speaker of today's DM Bose Memorial Lecture. As we all have heard that Professor Bose was a very well-known scientist, extremely well-known scientist who had significant contributions in the field of cosmic rays, radioactivity, neutrons, etc., and was associated with many institutions, and of course he was the director of this very esteemed institution, namely Bose Institute. Now, today's speaker, Professor Roychaudhuri, needs no introduction to this audience, because I'm sure that, like me, many in today's audience were his students and were inspired and fascinated by his classes and lectures. I have no hesitation in acknowledging that Professor Roychaudhuri has a very big contribution in shaping my physics thoughts, which I learned during my master's classes from him as well as during my research career. Professor Roychaudhuri did his PhD from University of Maryland with Professor Greenberg, after which he did his postdoc in University of Oxford and EIFR Mumbai. He joined Science College, after which actually we became his student, and later became the Taroknath Malik Chair Professor. And he was also the director of HRI Allahabad for several years, after which he joined Calcutta University again. Professor Roychaudhuri has pioneering contributions in the field of high energy physics, for which he received numerous prestigious awards, including Shanti Swarup Bhattagar Award. He is a fellow of all science academies of the country. Professor Roychaudhuri's specialty is that he worked in a very vast spectrum of areas in particle physics, such as electroweak theory, CP violation, supersymmetry, extra dimension, neutrino physics, all. And in every direction, his contributions are recognized with huge citations and acknowledgement. One of the very special aspects of his career, in my opinion, is that he single-handedly developed a brilliant research ambience in Science College with his very brilliant research students, and he has kept a great legacy of research activities in particle physics in Calcutta, sitting in a university setup which, of course, has the lesser facilities. This was truly an example. Professor Roychaudhuri's contribution in neutrino physics is internationally acclaimed, and today he will give us his perspective on this very special area, which we all know is one of the most active research area in the field of particle physics. I therefore invite Professor Roychaudhuri to deliver the D.M. Bose Memorial Lecture 2021. Professor Roychaudhuri.
Thank you very much, Professor Sengupta. Professor Sengupta has said many good words about me. I don't know whether I deserve all of them. I'm trying to share my screen. I'm having some problems, but let me see whether I can work it out. Just a minute. Give me a minute. Okay. Now to go to half the entire screen. A window. Let me see whether I can get there. Yeah, very good. Very good. Is anything visible at that end?
No, not yet.
Not yet? Just a minute. Should have been. Okay, now perhaps. Is the screen visible now?
No.
But here it says it is sharing, and I can stop the sharing.
Now it is coming. Now it is coming.
Now it's coming? Okay.
Yeah. Now you can just kind of enlarge it.
Yeah. Okay. So it's a great honor for me to be presenting this D.M. Bose Memorial Lecture. Professor Bose, of course, was the director of the Bose Institute, but in addition to that, he was a brilliant scientist, and to speak in his honor is really a privilege for me. The points, the topics which I wish to cover today tend to show that the role of mass is extremely important in various directions in particle physics, and I understand that the audience is very mixed. So I have tried to discuss the issues at a very broad level without going into too many technical details. So the question first that will arise is, what is mass? And I will briefly touch upon the equivalence principle. Then we will go on to discuss the mass of an elementary particle. Now these, on this side, these are the elementary particles that we know today. Namely, the red colored quarks and the yellow colored leptons. The quarks have strong interactions which the leptons do not. These are all fermions, and in addition to the fermions we have the bosons. These are spin 1 bosons, the photon, the gluon, the Z boson and the W boson. These are the mediators of the forces, and we have to discuss how the masses of these are all generated. We talk about the fermion masses and the gauge boson masses, namely the masses of the quarks and the gluon, not the gluon, but the Z boson and the W boson and so on. And for this, the Higgs mechanism will become very important. And this is something which the Higgs boson was found in 2012, and that's a major step forward in particle physics. This leads to the Standard Model, which I briefly mentioned. And then the Standard Model, though it is very elegant, it has a few shortcomings. And one of the shortcomings which has been brought into focus is that the Standard Model says that the neutrino is a massless particle. But now we have evidence that the neutrino in fact has a non-zero mass, so we discussed that. And then the possibility that the neutrino is in fact a Majorana fermion. We come to that, and towards the end, if time permits, I briefly touch upon dark matter and dark energy before I look ahead. But before I get into the body of the lecture, I want to remind ourselves, even though perhaps it's completely unnecessary, a little bit about Professor D.M. Bose. Professor D.M. Bose is he was a very pioneering scientist of a very diverse interest. He studied, he's a nephew of Sir Jagadish Chandra Bose, and he studied at D.M. Bose, he studied at Presidency College, and then at Christ's College, Cambridge, and also at the Royal College of Science in London. And he got his, then he came back to India and was a professor at Calcutta University, and then he went on leave and went to Berlin, where he obtained a PhD in 2019. His PhD was delayed due to the First World War. The positions which Professor D.M. Bose, which he held, include the Rashbihari Ghosh Professorship at Calcutta University, then the Taroknath Palit Professorship of Physics, also at Calcutta University. He became the Taroknath Palit Professor in 1935 when Professor Raman moved to Bangalore. And then after a few years, when Sir J.C. Bose passed away, Professor T.M. Bose took over as the director of the Bose Institute. This was in 1938, and then he carried on in that role till he stepped down in 1967. He had many additional responsibilities, and I have mentioned just a few. He was the president of the Asiatic Society, he was the editor-in-chief of Science and Culture, and various other things which I do not even mention. His research highlight, which was already ascribed to by Professor Bandyopadhyay, one of the contributions, he had several other contributions. He was an expert on cloud chambers and things like that. He worked on physiology of following the tracks of his uncle, Sir J.C. Bose, various other things. But the one work which ties up in some ways to this lecture is the one which he carried out with his student Vibha Choudhury. This work was very novel in that they exposed photographic emulsion plates to cosmic rays at high altitudes, and they carried out these experiments in the period 1939 to 42. And they devised a technique by which, through the cracks in the photographic emulsion, they could find out how the particle passing through the emulsion interacted with the emulsion plate, and how it got scattered, and from the track length and from the scattering, they devised a way by which they could determine the mass of the particle. Now, at that time, it was known, the proton was known, the proton and the neutron, these were known, the electron was known, and before that, before 1939, the antiproton had already been found. The alpha particle was known, of course. But what they found in their emulsion plates, in addition to these particles which are there in cosmic rays, they noticed that there was a particle whose mass they identified in terms of the mass of the electron, ME, as it's 216 plus or minus 40 times, plus or minus 40, 216 plus or minus 40 times the mass of the electron. The mass of the electron, as we know, is about half an MeV. So therefore, if we translate this to MeV energies, so this would be 108 plus or minus 20. So that could be, this could be therefore either a pi plus minus, whose mass is 139 MeV, or it could be a mu plus minus whose mass is 105 MeV. Unfortunately, Bose and Choudhury, they could not reduce the error bars here because of the limitations of the emulsion plates that were available to them. Afterwards, Powell in 1945 determined these two masses with better emulsion plates, so he could distinguish among the pi plus minus and the mu plus minus, and showed that there are these two components which are there, and with his better emulsion plates, he determined their masses. And unfortunately, as I said, Bose and Choudhury, they missed the Nobel Prize because at that time they did not have access to the best emulsion plates, which is very sad indeed. But certainly the work itself was path-breaking, and it's in the tradition of others, like, for example, C.V. Raman and Meghnad Saha, and Sir J.C. Bose, and S.N. Bose, that they could do path-breaking work sitting in India. It's very, very inspiring indeed. Let me now get back to the topic of my lecture. And first we talk about mass itself. Now, mass manifests itself in two completely different ways. One way, as we know, is in the gravitational force, where the mass enters in this expression as a product of the two masses between which we look for the gravitational force. It's an inverse square law of force, and there is a coupling constant. There's the Newton constant which enters here. And another place where mass enters is in Newton's second times the acceleration. So in principle, these are completely different things. One is what determines the strength of the gravitational coupling, and the other determines the reaction to force. Now, it turns out that is there some difficulty with my presentation?
Is it possible to switch off the microphone at Bose Institute?
Sorry, to switch on?
Switch off the Bose Institute microphone. Yeah, now it is done. Okay. I think it will be okay.
Okay. So, there are these two independent kinds of masses, the gravitational mass and the inertial mass. And it's a remarkable result, which is called the equivalence principle, the principle states that the gravitational mass is the same as the inertial mass. It's the same thing as the inertial mass. Now, this makes this leads to a very radical consequence, because if a particle is moving under the force of gravity, then the mass in fact drops out, it cancels out. So supposing that the particle of mass m is moving in gravity, so let's say this m2 is then m, and then if we calculate the acceleration, then the m will drop out because the acceleration is the force divided by the mass. So the mass will drop out. So therefore the acceleration will be the same irrespective of the particle itself. So in other words, under gravitational force, all particles will move in an identical fashion. So the motion of a particle under a gravitational force does not depend on its mass. Now, if it does not depend on the mass of the particle, what else could it depend upon? All particles are moving in the same manner under gravity, so therefore that must then be a property of space-time itself. So space-time must determine the nature of motion under gravity. Now this is a cornerstone of the general theory of relativity. Of course, how the curvature changes with the mass, etc., that is another important ingredient. But the equivalence principle tells us that all particles would move in the same manner. Another way to look at the equivalence principle is that when some body is accelerating upwards, then it's the inertial mass which determines the force, whereas if it's falling freely, then it's the gravitational mass. Be that as it may, we now wish to look at the origin of mass of elementary particles. Now, normally for a particle, when we talk about its mass, we can think of multiplying the density by the volume. But for an elementary particle, which is point-like, this formula will not work, and the mass must originate from some mechanism. And what could that be? That mechanism must be through the interactions of the particle. So this is a quote attributed to Feynman, that the origin of mass is due to inertia, is due to interactions. Mass is a measure of inertia, and if there is more interaction for a particle, then it is difficult for it to move, and the more there are interactions, the more is the mass of the particle. Now, as we go to the next step, it would be useful to remind ourselves about the two kinds of particles that we have in nature, the fermions and bosons. The fermions and bosons are distinguished by their spin quantum number. This is an intrinsic property of the particle, and it is measured in units of h over 2 pi, which is often called h bar. H is Planck's constant, of course. So in units of h bar, bosons have integral spin, while fermions have half integral spin. So according to quantum mechanics, the spin of a particle is either half integral or integral, and the half integral spins, they are fermions, and they satisfy an exclusion principle, which is at the root of, for example, the atomic structure. On the other hand, bosons can accumulate in any state, in any number, and this leads to things like Bose-Einstein condensation, or as we'll see in a moment, the properties of the Higgs boson. At this point, let us talk about the intermediaries of force, what I have mentioned before as gauge bosons. So what are these things? There are these basic particles, the up, down, the charm stop, the charm string at the top and the bottom. These are the quarks, and these are the fermions, and these are the leptons. And these, the things in the first three columns, these are all fermions, and the fourth column are the bosons, and the bosons are the intermediaries of the interaction. I have not included in this list the gravitational force, because as of now, we do not have a satisfactory understanding of the gravitational force as a quantum theory. So the gravitation is yet to be included. There are various possibilities which are being discussed, like, for example, string theory, which might be able to incorporate gravity in this framework. Another thing which has not showed up here is the Higgs boson, and that will have a major role in much of my lecture. So let's focus now for a moment on the force intermediaries. The electromagnetic force is due to the exchange of a photon. Einstein has told us that it's not possible for one particle to exert an effect on another particle at an arbitrary distance instantaneously. So in fact, any interaction is due to the exchange of some particle, and in this case for electromagnetism, it is the exchange of photons. Now, every interaction has its own force mediator, and the photon, who is the mediator of the electromagnetic force, is a massless particle. The range of an interaction is inversely proportional to the mass of the mediating particle. So the fact that the photon is massless implies that electromagnetism is of infinite range. But not all interactions are of infinite range. In fact, the weak interactions which act within the nucleus, the weak interactions are short-ranged, which means that the particle which is responsible for the weak interactions, which I call the W, must have a large mass for it to be short-ranged, according to this formula, that the range is inversely proportional to the mass. So what does the W boson typically do? The W boson does the following. For example, in beta decay, a neutron goes to a proton and the charge is changed. The neutron has no charge, of course, electric charge. So it becomes a proton with the emission of a W minus, a negative charge particle is emitted, which then decays to an electron and an antineutrino. So this is the Feynman diagram of beta decay. And the beta decay is represented by this typical process. Of course, in a nucleus, the neutron is a part of the nucleus, so there's a daughter nucleus and so on. The more important thing here is that the exchange particle is the W boson, and the W boson is heavy, and it has a mass of around 80 times the proton mass, 80, something around that. Now, all these interactions, the electromagnetic interaction, the weak interaction, the strong interaction, they can be put in a very nice framework called gauge symmetry. Gauge theories are ways through which interactions can be explained. I do not go into the details, but we now have a very good understanding of what the basic particles are, and how they act, what are the forces which act in them. And these are all of a certain type. They are called, they obey the gauge symmetry principle. And the gauge symmetry principle has many good features like high energy behavior and so on. So it's a very attractive possibility which makes things calculable and predictions are possible and so on. So things look bright, except that there is a major handicap. The major handicap is that the symmetry has a price. All particles, the fermions like quarks and leptons, as well as the bosons like the W and the Z, must be massless. Now that's a very heavy price to pay. Of course, it's good for the photon. The photon is massless, so it's the gauge symmetry imposes that constraint, which is very good. However, this is not in agreement with reality, because quarks and leptons and W bosons and Z bosons, these all have mass. So something must be missing. What is missing? What is missing is that is called the Higgs field. The Higgs field is an entity which breaks the gauge symmetry. But it breaks the gauge symmetry in a very subtle fashion. In a fashion such that the good features of the symmetry are preserved, and yet the good features, meaning the high energy behavior and so on, the predictions and things like that, they continue to be there, and yet particles become massive. The Higgs boson is a wave in the Higgs field. The Higgs bosons have been detected at CERN. These ideas were propounded by Higgs, Peter Higgs, and Prout and Engler, and also others like Guralnik, Hagen, and Kibble, and a few other people. Similar, Anderson had similar ideas in condensed matter physics. So Higgs and Engler, they got the Nobel Prize for this work. By the time the Nobel Prize was given in 2013, Prout was no longer alive. So Prout missed it out. Now you might wonder that for such a path-breaking step, the paper of Higgs or the paper of Prout and Engler must include a lot of very technical material. No, that is not at all the case, and here is the paper of Peter Higgs in its entirety. So this is the paper. It's 1.5 pages, number one. Number two, what does the paper contain? It's a classical field theory analysis of small oscillations. Now, we teach it in the MSc class these days, of course, but it is accessible to even an advanced undergraduate who has an introduction to the theory of small oscillations. And this is, of course, Mr. Peter Higgs. Now, you might think that for this 1.5 page paper dealing with small oscillations, how can Peter Higgs win the Nobel Prize? Well, that is because of what is said here in the title, broken symmetries and the masses of gauge bosons. Broken symmetry is a very novel idea, and as a part of that idea, Higgs had to suggest this very, very radical proposal that the vacuum, which we always thought had nothing in it, he said that the vacuum is in fact not empty. It is filled with what we now call, it is filled with the Higgs field. That is a very, very radical proposal. Now, I would not be able to go through the steps of this calculation, though they are very easy, and all of you will easily go through these steps. There's not much material in it. But I'll go through the Higgs mechanism through a few cartoon shots. So, how does the Higgs mechanism work? Imagine that there is this crowded room, and there is some VIP, a lady who enters through this door, and she has to go through the door, through the room, and exit from a door on. Now, if the room had been empty, she would have gone right through without any problem, without any difficulty, but because of the crowd, she has to, her bodyguard, so to speak, have to nudge and push and so on, and they have to make way for her to go through the room and go out the other way. In effect, her inertia has increased because of the crowd in the room. This is precisely the mechanism which happens for elementary particles. In the case of elementary particles, the vacuum of the universe is not empty. It has a background, what is called a condensate of the Higgs field. And this is responsible for particle masses. That is, the particles have difficulty going through the Higgs field, and because of their interactions with the Higgs field, their mass is generated. Particle masses are proportional to their strength of coupling to the Higgs field. Now, the photon does not couple to the Higgs field. So, as far as the photon is concerned, the vacuum is empty, and therefore the photon does not get a mass due to the Higgs field. But the other particles which do interact with the Higgs field, they become massive. Now, how can we know about this? This is an idea that the vacuum is filled with the Higgs field, but how do we know that it is actually the case? And that can be known, that can be understood by another cartoon. And here, let's say here is this, and he says, do you know elections are now going on in Tripura? And so here is this crowd of people, the same crowd of people, and they're told that elections are going on in Tripura. So once the first person hears that, and then he tells the next person, and the next person whispers it to the next person, and so on and so forth. So the statement that elections are now going on in Tripura passes first person to the second person, and so on, and it goes through the room. There's no human being, no VIP entering the room. So it's like a wave in the crowded room. And that wave in the Higgs condensate is what is Higgs field. So it's the rumor which is passing from one person to another, and the rumor travels like a wave in the medium, and a disturbance in the Higgs condensate Higgs boson. And this was detected at the CERN Large Hadron Collider in 2012. Now, once the Higgs boson is there, the standard model becomes complete. The standard model requires that we have fermions and bosons with mass. And I have to pause here for a moment to discuss the masses of fermions. The fermion is usually represented by, in the Dirac equation, by a spin field, psi, and it has two components, the left component and the right component. An easy way to remember these two components is to recall that a fermion has associated with it two vectors. One vector is its momentum, so this is the momentum vector, and the other vector is its spin angular momentum. Now, the spin angular momentum could be parallel to the momentum, or it could be anti-parallel to the momentum, and this is what we call the right-handed or left-handed. So there is the left-handed fermion and the right-handed fermion. Now it turns out that the fermion mass couples left to right. So therefore the fermion mass is this kind of an interaction. The right fermion couples to the left fermion, or the left fermion couples to the right fermion, and left goes to right under parity. Now, if there is only the left-handed component or only the right-handed component, then of course the mass term vanishes because it involves both components, the left and the right component. Why does it do so? That we can imagine by looking at an example, at this example. Supposing that a particle has a non-zero mass. So it's a massive particle and it is moving, it's moving in some direction, then its velocity can be large, but it cannot be the speed of light. So we can always imagine a frame of reference which is moving in the same direction, but is moving faster than the particle. Now, if in that frame, in that reference frame, the particle would appear to move backwards, but spin would not change direction. So therefore, if the momentum reverses and the spin doesn't, then a right-handed particle becomes a left-handed particle. So therefore, for a massive particle, we must have both left and right-handed components in order to be consistent with relativity. Now, if there's only left or only right, then we cannot go through this argument. Of course, the argument applies only if the mass is not zero. If the mass is zero, then the particle is moving with the speed of light, and in that case, we cannot go to a frame in which the momentum direction is reversed. Okay, so now taking all this into account, the standard model does the following. The standard model describes the strong and electroweak interactions, and the forces are mediated by the gluons for the strong interaction, and the W and the Z bosons for the weak interaction, and the photon for electromagnetism. There is parity violation in the weak interactions, and that is due to the asymmetry between left-handed and right-handed fermions. They behave differently. The right-handed fermions do not couple to the W boson, for example, but I'm skipping those technical details. The masses of the W, the Z, the quarks and leptons are all obtained through their interaction with the Higgs field. And there's of course also the Higgs boson, the signal, the key signal for the standard model. There's one other point which I want to touch upon now, which is that in the standard model as formulated, there is no right-handed neutrino. And there is no right-handed neutrino, which means that the neutrino, as we discussed, must be massless without the right-handed component. And this was chosen in the standard model for consistency with information of that era. At that time, it was believed that the neutrino is massless, but now we know that this is not true. So I come to neutrinos, and how do we know that neutrinos are have masses? Well, the neutrinos are very difficult to detect. They hardly interact. They pass through the Earth. They pass through lead plates very easily without interacting. And they're also harmless because of that reason. They do not interact with our body, but that makes them very difficult to detect. And intense sources of neutrinos are required, and very huge detectors are required. Chances of a neutrino interacting with one proton or one atom is small, but if we throw a lot of atoms in its path, then might interact with one of them. So to increase the probability, huge detectors are constructed, and neutrino experiments are carried out using those huge detectors. Neutrinos have two kinds of interactions, the W boson mediated weak interactions and the Z boson mediated weak interactions. Neutrinos are uncharged. They do not have an electric charge, so they do not interact with the photon. Most properties of the neutrinos have been discovered in the past 2 decades. And the important point made here is that an electron neutrino on interaction will produce an electron. A muon neutrino, on the other hand, will produce a muon. And the third kind of neutrinos, the tau neutrino, will produce the tau lepton. For a Z boson mediated interaction, the initial and final neutrinos are the same. This is a W boson mediated interaction. For a Z boson mediated interaction, a neutrino remains a neutrino. No change happens. Nothing happens. How do we know that neutrinos have a mass? That is through oscillations. We have found that neutrinos oscillate. How do we know that? In the sun, there is fusion reaction which takes place. 4 protons fuse to form a helium nucleus and 2 positrons, 2 neutrinos, and 27 MeV of energy. This energy is responsible for the heat and light from the sun. And the neutrinos are also there, they're coming from the sun. These are called solar neutrinos which are reaching us. And unlike the sunlight, the solar neutrinos are reaching us day and night. Because in the night time, the photons cannot reach, the sunlight is blocked by the earth, but neutrinos can pass through the earth and they appear on the other side from the bottom, from inside the earth, the neutrinos come out. So the neutrinos come all the time. Now the number of neutrinos that are coming from the sun as a function of the neutrino energy is very well calculated. There are several reactions which take place, and we know we have a very robust prediction of the number of neutrinos. This is a log scale, so therefore the number of neutrinos goes up very fast for the PP reaction, but these are low energy neutrinos which are harder to detect. The boron neutrinos, which have higher energy up to 20 MeV, they are easier to detect but much less in number. Remember, this is a log scale. Anyway, what are the results regarding solar neutrinos? And I ask you to focus on the second column. The rest, these are details of the different experiments. The second column tells you the number of neutrinos observed over the prediction. Now, the prediction is quite robust, and if the observation agreed with the prediction, this ratio should have been 1. But notice this ratio in the 4 different experiments, in fact, several different experiments which I have listed, are all far away from 1. They are not consistent with 1 within many, many error bars. So therefore, there's a serious issue here. There are many, these experiments differ in their technique. They have different thresholds of energy. Unless the neutrinos have more than the threshold energy, they are not detected. And in spite of all of this, all of the experiments see a very significant depletion of neutrinos. Now, Mr. Davis, Ray Davis Jr., he was the first one to start this experiment at home state in 1968. And the reaction that he used was neutrinos interacting with chlorine, produced argon and an electron. And the argon is a noble gas, so it doesn't interact very much. So he kept the detector inside, and then he pulled out the detector after 2 weeks and counted how many argon atoms were produced. Very difficult experiment to count atoms, but argon goes into a radioactive mode, so through the photon emission, the argon can be counted. Mr. Davis has a background in chemistry, and when he came out with this result first in the late 60s and 70s, people laughed at him and said that chemists should not have anything to do with physics. But of course, Mr. Davis had the last laugh because his result was proved right by other experiments and he won the Nobel Prize. And the Nobel Prize was not in chemistry, but in physics. So that was a good way to pay them back. But how was this established? It was established because there are two ways to explain these shortage of neutrinos. One way is to predict that neutrinos are probably somehow decaying to other particles and are not seen. Another way to interpret it is to say that perhaps neutrinos have oscillated to some other kind of neutrino. Only electron neutrinos are produced in the sun. But if the electron neutrino somehow manages to oscillate into a muon neutrino or a tau neutrino, then the detectors will not see them and then the number will be depleted. How do we distinguish whether the neutrinos have decayed or they have oscillated? If they have decayed, they are lost, so the count will always be less. But if they have oscillated, and if we could do an experiment with the Z boson, which uses the Z boson, then the Z boson has the same interaction for all kinds of neutrinos. So that would not show a depletion. So therefore, an experiment was mounted which used the Z boson as a mediator, and this is called a neutral current experiment, the Snow neutral current experiment. And lo and behold, the Snow neutral current experiment found that there is perfect agreement with theory and observation. So in fact, no neutrinos are lost. They have only changed their type from electron type to some other type. So what is this oscillation mechanism? The oscillation mechanism works like this. It's a quantum mechanical phenomenon, and it relies on the superposition principle. It's just like the oscillation of a pendulum from one end to the other and back again. Here an electron neutrino becomes a muon neutrino and then back to an electron neutrino and so on. So here the red line represents an electron neutrino and the blue line the muon neutrino. So this is 1 in the beginning and this is 0, and then as time passes this becomes 0 and that becomes 1 and so on. The total remains the same, but the fractions continue to change. The oscillation probability of an electron neutrino going to a muon neutrino has a formula like this, where theta is some mixing angle, which is relevant for this issue, and then lambda is the oscillation length. It is the length characteristic of this discussion, and the oscillation wavelength goes like this. It is proportional to the energy and inversely proportional to delta. Delta is the difference in the mass squared. If the mass squared difference goes to 0, if delta is 0, then lambda becomes infinity, and then we'll never be able to see oscillations. Contrarily, the fact that we do see oscillations implies that delta is non-zero, and that implies that neutrinos have a non-zero mass, which is a very important result because it tells us that there's something more than the standard model. I have another 2 or 3 slides. Is it possible to finish, Professor Sengupta? Maybe another 10 minutes or so?
Yes, you can.
Okay. So the neutrinos have a mass. The question now is it possible that the neutrino is its own antiparticle? Of course, a charged particle cannot be its antiparticle because the antiparticle must have opposite charge. But a neutral particle can, in principle, be its own antiparticle. The photon is its own antiparticle. For example, there is no antiphoton. Or the pi 0 is its own antiparticle. There are no fermions that we know which are which are self-conjugate, but maybe the neutrino is. Now, if the neutrino is its own antiparticle, then the following novel process will take place. There is something called a double beta decay, which is like beta decay, but that it's a two electron emission along with two neutrinos. This is what is called a double beta decay. Now, if the neutrino is its own antiparticle, then some of the time a nucleus which undergoes double beta decay will also have this kind of decay, which is neutrino-less. X goes to Y plus 2 electrons. Now, whether this process happens or not depends on the mass of the neutrino. In fact, it's proportional to the square of the mass of the neutrino. Neutrino-less double beta decay, whether it happens or not. How do we know that there is neutrino-less double beta decay? What is the experimental signal? For that, you have to go back to the original way in which the neutrino was proposed. The neutrino was proposed because in beta decay, there was a lack of conservation of energy. And the electron came with the distribution of energy. The one electron in beta decay came with the distribution of energy, and so the neutrino must have carried off the other part of the energy. Now, if neutrino-less double beta decay does take place, then there is no neutrino taking away any energy. So then the energy of the two electrons must precisely be the difference in masses of the parent and the daughter nuclei. So therefore, there will be a peak in the invariant mass, invariant energy of the two electrons, exactly at the difference of the masses of X and Y. So therefore, the way the experiments are performed is to look for a peak in the two electron total energy. At this moment, no positive signal has been found, which establishes an upper bound on neutrino masses of less than 0.2 electron volt. Okay, finally, masses have other roles in particle physics, in astroparticle physics, and in cosmology. One of them is dark matter. And what is dark matter? Dark matter, the evidence for dark matter is from various sources, including the cosmic microwave background radiation. And the one which is often quoted is this from the galactic rotation curves. If you look at a galaxy and the different stars in the galaxy, then you expect that the velocities of the stars in the galaxy will form a distribution like this, which peaks at the galactic size. The galactic size we can estimate from the visible matter, and it turns out, in fact, experimentally it is observed that the velocities in fact show a flat behavior till further out, quite significant distances. Now what this means is that Kepler's laws are not holding, which means that the mass which we see is not what all is there. There is some more mass, but it's not a visible mass. So this is called dark matter, and particle physics has several candidates for dark matter. They have to be stable, and they have to be almost non-interacting, because otherwise you would have seen them. There are many experiments going on to look for dark matter. Supersymmetry provides a candidate for dark matter very naturally. Kaluza-Klein models with extra dimensions provide dark matter candidates, but we have not seen any dark matter, and none of the theory predictions can at this moment be tested. Another ingredient which is still quite an open one is dark energy. Dark matter can be clumped around galaxies and clusters of galaxies, but evidence points to some energy distributed uniformly in all space. And in fact, this is the dominant part. What is the evidence for dark energy? Well, there are many evidences from distant supernovae, from the anisotropy in the cosmic microwave background radiation, from structure formation and elsewhere. The particle physics interpretation of dark matter, dark energy is at the moment lacking. So, how do we know that there is dark energy? What is this acceleration business? Well, we can have a kind of picture of this from the example of a ball thrown from the ground upwards. Now, when we throw a ball upwards, then its velocity gradually decreases until it comes to a stop, and then it starts falling back. So, in a similar way, the universe is expanding from the Big Bang, and there is a gravitational attraction of matter on the universe. So, we expect that it will gradually slow down. But in fact, what is observed is that acceleration was in fact less earlier, not more. Acceleration is not reducing, but it's increasing. So there's something more that's happening, and this is an indication of dark energy. It is what Einstein had introduced. Remember, Einstein, in order to stop the expansion of the universe, proposed the introduction of a cosmological constant, so that would effectively block the expansion. In a similar way, this dark energy has now been introduced. We lack a proper explanation of dark energy so far. So, to look ahead, there are many manifestations of mass. We still do not know, we do not have a satisfactory theory of quantum gravity. There are alternate theories of gravity which go beyond the general theory of relativity of Einstein. Is there physics beyond the standard model? There surely is, because neutrinos have a mass, and then there are other issues for which the standard model has no satisfactory explanation. For example, the baryon asymmetry of the universe, or the dark matter and the dark energy in the universe. So there must be some physics, but how to test them, how to look for this new physics? It's actually quite disappointing that the Large Hadron Collider has so far given us no evidence for physics beyond the standard model. We have to understand neutrino masses. Many neutrino mass models are there. However, it's hard to distinguish one model from another. And this is an open area of much research. Neutrinos are Majorana fermions. Are neutrinos Majorana fermions? If they are, then lepton number will not be conserved, and that itself will have other signals which have to be looked for. There are many experiments worldwide. The Large Hadron Collider, about which we all know, the B factories, which produce B mesons in huge numbers. The one running now is in Japan. And then the Large Hadron Collider also has a B physics experiment. And then the DUNE is a neutrino experiment being set up in Fermilab in the US. India has its own program, the India-based Neutrino Observatory, which is unfortunately stuck in legal quagmire. One hopes that it will take off very soon. And then there are these questions: what is dark matter and what is dark energy, which one has to look for answers to. Thank you very much. Thank you.
Professor Roychaudhuri for this wonderful introduction to masses. The most fundamental concept that we start learning from our school days, what are masses? I mean, you get a detailed description. I will give you a summary of that. What Professor Roychaudhuri has taught us today. But before that, I heard that some students want to ask some questions. So, can I take the questions? Professor Roychaudhuri, is it all right?
Yes, of course, yes.
So, can the questions be coordinated?
Hello. Thank you very much, sir, for this beautiful talk. So I would like to ask about the neutrino masses that you have said that from the neutrino oscillations we can say that the neutrinos are not massless, they do have mass. Then we should also expect to see a signature of right-handed neutrino, right, sir?
Yes.
Okay, so could you please explain or elaborate on more on that? That is there any experiments going on to explore that, or what's the main limitation or difficulties to get the signatures of the right-handed neutrino? Why we don't see that?
Okay. The neutrino mass models that we have all introduce right-handed neutrinos some way or the other. Now, there's something which I did not touch upon. Thank you for asking me this question. Neutrino masses turn out to be very, very small. The mass differences are extremely small, and they are so the masses, the neutrino masses, will have to be so tiny that it would be very unnatural to have neutrino masses in the same manner as the masses of all quarks and leptons. So different ways have been devised, usually what is called the seesaw mechanism. And the seesaw mechanism not only introduces right-handed neutrinos, but makes an arrangement in which the smallness of the neutrino masses emerges naturally. So current experiments are trying to test the seesaw mechanism, and it is hoped that they will be able to tell about masses of right-handed neutrinos. There are some models which are extensions of the standard model, like the left-right symmetric model, where the right-handed neutrino is a very natural ingredient. Now, if such a neutrino is found, then it will decay because it will be heavy, and those properties, how to find a right-handed neutrino, what will be its signals, those have been elaborated upon by theoreticians, but experiments have so far not yet been able to find any of the signals. It's an open question on which work is going on.
Okay, sir. Okay, sir. Thank you very much.
So, is there any other question? Is there any other question?
I am Juba Gupta. I am actually a nuclear physicist. So I would like to ask you questions regarding beyond standard model stuff. So we have a very well-known problem as cosmological lithium problem in nuclear physics. Now recently there has been some work to explain why these lithium abundance anomalies there for the past 40 to 50 years. And some recent works actually predict that the lithium destruction through beryllium is carried out by the emission of an X particle, which is of mass around 16 MeV, and that may be a candidate of dark matter particle. So, could you please comment from a particle physics aspect of this? I mean, regarding the mass, it's around 16 MeV mass particle. It's a neutron boson that's been predicted, and which might explain the cosmological lithium problem.
Unfortunately, there is a lot of echo in your question. Professor Sengupta, could you hear the question properly? Can you tell me what the question was?
No, I couldn't. The same thing happened here also. A lot of echo. So, can you ask the question again? I all needs to start off their microphone. Then probably your voice can be heard.
The first question was very clear. What was wrong with this question? The first question was absolutely clear. There was no issue. No, we cannot hear you. Can you use this?
Closer to your mouth, slightly closer to your
Or
mouth.
maybe the same mic. Is it the same mic? Same microphone. I understood it was a question on dark matter, but
Can you hear me now?
yes, now I can hear you.
Okay, so I changed the microphone. Yeah. Okay, so my question is that we have a very well-known problem in nuclear astrophysics, which is the cosmological lithium problem, right? So where there is a well-known anomaly in the lithium 7 abundance, which could not be explained for the last 50 years maybe. So now recently there has been some work which actually says that there is a particle like, I mean, they say that it's an X particle of mass around 16 MeV, which is being emitted from an excited beryllium-8. This particle might explain this abundant neutral boson. A recent work says that. So can you comment from a particle physics point of view the mass of this neutral boson? I mean, and people say that it might be a dark matter candidate.
Okay. No, unfortunately, I am not familiar with this work that you cite, but it's possible. Right now, there are various other. Usually, the normal way to look at dark matter was that dark matter is a heavy particle which is weakly interacting. That was the normal way.
Yeah.
But now, since much of that region has been excluded, people are focusing on light dark matter.
Okay.
And so a particle in the 10 or 20 MeV region would fit in the dark matter category. And both fermions and bosons are being considered. However, without knowing the specific model, it is difficult to comment because it's one thing to suggest that there is this dark matter candidate at 20 MeV, but the other thing would be, or 15 MeV, the other thing would be to suggest tests for the model. And if there are tests which can be carried out, then surely it will be. There's no question.
Any more questions from anybody? Please, sir. The microphone is not working. Can you? Microphone? Yeah, it is not audible. Can you?
It's not audible. Microphone is not working.
No, it is not working.
No.
Is it working now?
Very feeble. I mean,
Hello?
The previous microphone worked very well. Sorry, we cannot hear you. There's a problem.
think there is some problem.
But it was clear for the two, yeah. Now we can hear.
Can you So, can you speak in your... No, you are not audible.
Hello. Is it audible now?
Yes, it is.
Okay. So, sir, you made a comment that it is a matter of kind of uneasiness that LHC did not give any hint about something beyond standard model. So, do you think there is something missing in the experimental program there, or you tend to believe these results that there is nothing beyond standard model?
Sorry, please. It was a little better towards the end. You are asking about an experimental program.
Is it
Yeah.
better now?
Yes, a little better.
I said that you made a comment that it's a matter of uneasiness that LHC did not give any hint about beyond standard model. So do you think that there is something missing in the experimental program which is unable to address beyond standard model things, results, or you tend to believe the experimental results coming out of LHC and that there is nothing beyond standard model?
Yes, I got the question now. Thank you. Thank you. There is a lot of activity in beyond the standard model physics. The first and most important one was supersymmetry. There are many models of supersymmetry. Now, of course, one can test only models which make predictions whose results can be tested in the current round of experiments. The Large Hadron Collider is a particularly good one for testing beyond the standard model physics. And so far, the Large Hadron Collider has ruled out many of the beyond the standard model predictions. So it's tightening the beyond the standard model physics, but one can never rule it out because it's asymptotic. That is, you can go up to this much, but there will always be something beyond that. It depends on how much energy your accelerators have, what is their luminosity, their cross section, and so on. So up to the present limit, there is no beyond the standard model result which has been found, but one hopes that it will be. Neutrino mass is an indication. There are a few indications in the decays of B mesons. So one hopes that there is some physics beyond the standard model, and one also hopes that there will be direct evidence will be detected, but at this moment nothing has been found.
So, any other questions from the audience? Any other questions? There's no other question? Okay. Okay, so if there is no other question, I think last, the last question that probably was trying to ask that whether there is any observational belief that there is some standard model or there is some theoretical compulsion that would look beyond standard model. Now, just I have a couple of questions. One is the context of Higgs mass that large radiative correction, that problem, and problem to that Higgs vacuum expectation value that is filling up the entire universe produces a very large cosmological constant. Whether these two are very strong theoretical compulsion to think beyond standard model.
I completely agree. I do completely agree. The cosmological constant is a major challenge. And I think it's a bigger challenge than the first point which you made, which has to do with the naturalness issue.
Yeah.
I think the cosmological constant, the size of the cosmological constant is a total mystery for us. Yes, certainly. Beyond the standard model physics is also called there, and perhaps, but one doesn't know, perhaps if we have a quantum theory of gravity someday, then that may at the same time address these issues. Yes, absolutely. They are very strong problems.
Right. So, I mean, in summary, the standard model cannot go beyond the quantum gravity scale, right? That we know for sure.
Absolutely, 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 absolutely.
So, I mean, I need to just summarize that it's once again a wonderful talk, because mass is probably the first word that we hear when we start studying physics in our school days, but it is probably one of the most difficult concepts that we do not realize at that time. But in this talk, we have learned how the apparently totally two different masses, one we learned from Newton's law of inertia, the other is the gravitation. They, through equivalence principle, they are identified, and also there is a great experiment from Galileo from the Leaning Tower of Pisa which establishes that. And then Professor Roychaudhuri described that how the mass can be described through interaction energy, that through in the domain of relativity, the mass energy equivalence. He introduced the concept of spin, then the concept of force as a mediating through particles. They beautifully described how the range and mass are kind of related, and therefore the interaction, like weak interaction, has to have the mediating particle have some masses. And with all this, he brought in the concept of symmetry, gauge symmetry, and then explained that how gauge symmetry can, in a kind of, unify this entire concept. But there's one problem of the mass of the particle again. And then the concept of symmetry breaking, Higgs mechanism, how it beautifully described the origin of the development of masses for the particles without really, hampering the main strength of gauge symmetry. And of course, then he went on to talk about fermion masses. Fermion constitute a very large part of the, you have seen the spectrum of particles, what he have described. And then, of course, came the most important problem of neutrino masses, described in the context of solar neutrino oscillations. Asked a very important question whether there is a Majorana fermion, and in this context related to double beta decay. And finally, the two other very important questions, namely dark matter and dark energy. So these are the most important questions now we are facing. He talked about quantum gravity very briefly. So this is, as a whole, is a beautiful perspective talk where we have kind of revisited the concept of mass. So once again, I learned many things again. So thank you, Professor Roychaudhuri, on behalf of everybody, and for illuminating us once again. So I became your student again today, and thank you for coming here. And I hand over to Professor Sarkar for to make concluding comments.
And Professor Roychaudhuri, all of us here at Bose Institute, the staff, the faculty, and the students, thank you from the bottom of our hearts for making time for us and coming and spending some of your valuable time. We apologize for the technical glitches that we have marred in your talk. And I'm sure there were many in the YouTube audience who had a lot of questions. But unfortunately, in the current format, we are not able to entertain those questions. We sincerely hope that sometime later, when we can physically meet, you will find time to come and spend time with us again, and then we can have a more interactive session. Thank you, sir. And thank you, Professor Sengupta, for helping us iron out the glitches of the technical problems that occurred. So, with that, ladies and gentlemen, we come to the end of today's session. The Bose Video Fraternity, thank you for being with us on this very special day. Please join us again on the 30th of November at 3 p.m. for the Acharya J.C. Bose Memorial Lecture. Best wishes to all of you, and goodbye from Bose.